Okay, we're gonna wrap up here the last bit here of this chapter and the class, I suppose, as well. So here we're talking about equilibrium in this chapter. We talked a little bit about rates of reactions as well. Remember again, sort of equilibrium situations involve reversible reactions, where if we have a reaction such as this. We have those arrows that once again sort of head in both directions, and in a reversible reaction, it really is sort of like a two-way street. A lot of times at the very beginning of the reaction, we have mainly reactants, and we have really the forward direction sort of happening where our reactants are basically coming together to make our products. At some point, usually in these sort of reversible reactions, you will sort of build up enough products that they will actually start to come back together, and actually they will head in the opposite direction, which is sometimes reversed to as the reverse direction, and make some reactants. So this is very different than sort of a non-equilibrium system, which is sort of like a one-way arrow where there's nobody coming back on the other side in terms of the products. Everything's just dumping out into the products. Eventually, a system like this will reach what is referred to as equilibrium or chemical equilibrium. And again, as we talked about, what that means is the rate of the forward direction will equal the rate of the reverse direction. So when something does reach chemical equilibrium, it again does not necessarily mean that you have equal amounts of everybody on each side of the arrows. It just means that as fast as the reactants break down to make products, the products will basically recombine and come back the other way and make your reactants. The result of that is you essentially, as we talked about, will lock everybody into place in terms of their concentrations. So they'll be able to maintain their concentrations as this equilibrium is happening. Also, if it happens to be gases, they'll be able to maintain their pressures as well. And when something does reach equilibrium, as we also talked about, it does look like sort of on the big picture aspect of it that maybe not much is happening, but there is a lot of activity happening, sort of super zoomed in on the molecular level, because there's reactants constantly breaking down the products, but we have products also going back to reactants. So there's a lot of activity that's happening, even though when you may look at your beaker or your test tube, it may just look like the reaction's over, but there's a lot of really forward and reverse sort of happening here to maintain sort of what you're seeing in that beaker. There is a relationship when we have these type of reactions that are reversible, which is known as the equilibrium constant. An equilibrium constant is capital K, and it is essentially the concentration of your products divided by your concentration of your reactants. So for example, here, if we were going to write the equilibrium expression for this guy, we would take the concentration of C to the coefficient as its exponent, times the concentration of D, also taking the coefficient as its exponent, divided by the concentration of A to its coefficient, and B to its coefficient as well. So we do use the coefficients here in the balanced equation to write this equilibrium expression, and it is a constant number. The only thing that will ever affect, for example, the equilibrium constant value is temperature. So if you change the temperature, you will have different value of the equilibrium constant. And that is between two different temperatures. So I guess what I mean by that is this: if you did a bunch of experiments with this reaction, and regardless of you started with all reactants in one experiment, you started with all products in the other, you started with a little bit of reactants, a little bit of products, it really will not matter. The proportion of products to reactants will always equal the same number, even though you may be starting with different amounts. And that's sometimes what people have a hard time grasping with the equilibrium constant is They think, well, in this reaction, I used like twice as much of my reactants than I did in the first one. How can I end up with the same sort of number at the end? And you will. So if you just think about a really simple explanation for why you can get the same number with different amounts is you just think about a fraction like 4/2, that equals 2. I could also get 8/4, which equals 2, which are different numbers, but they all come to the same sort of number at the end when you divide them. So you could actually start with various amounts of reactants and product temperature the same for all those experiments. You will end up with the same equilibrium constant value.
Basically use delta reactants to use delta products.
Yeah, so the proportion wise, it will always work out the same for that whatever reaction you're looking at in terms of how much products you have to reactants, basically, regardless of how much you start with. And again, that's why sometimes people, when they do this type of chemistry, have a hard time sort of thinking about that, because you think just, in your head logically, like, hey, I used a lot more in this reaction, I should get like a different sort of value at the end. But again, if you think about sort of the little fraction thing that I just did, there's many different ways that you can get to the number 2, basically, which is sort of the proportion there, and have different amounts of, say, reactants and products. So what I was talking about in terms of temperature is, so for example here, if we did this a bunch of experiments at 25 degrees Celsius, and let's just say we got a K of 10, for example, we could do as many experiments as we want at 25 degrees Celsius with different amounts of reactants, products, whatever it may be. And if you calculate the equilibrium constant, it will always pretty much be 10. Now, if you change the temperature, say, to 35 degrees, you might get a equilibrium constant value, say, of 20 or something like that. Now, if you keep the temperature at 35 degrees and do a bunch of different reactions, you will always get the same equilibrium constant at 35 degrees, which would be 20 every time. So when we talk about changing the temperatures, the only thing that affects the value of the equilibrium constant, what we're talking about is the comparison between the equilibrium constant value at 25 degrees and 35 degrees. They are different values, but if you stay at the same temperature, either 35 or 25, in this example, you will always end up with that same made up equilibrium constant value. So you always get the same value regardless of what you start with. This again is sometimes referred to as the Kc, as we talked about, which means concentration. So typically speaking here, that is going to be molarity that we're looking at, which is our moles per liter. We also talked about, I think, too, at the end there, that if you had all gases, you could actually write the same sort of equilibrium that deals with pressures, and it would be the partial pressure of C to the C, D to the D, divided by our partial pressure of A to the A, and B to the B here. And this is what is sometimes referred to as the Kp value. Again, P meaning pressures, so sometimes we do look at pressures in these type of things. The Kc and the Kp value usually, in most cases, are not the same numerical value, but they do tell you the same thing. So also a reminder that when you do calculate the value of K, K is just a number, no units. So if you have a large value of K, what that means is when you reach equilibrium, you should mainly have products present. So large value K means you mainly have products. And if you have a small value of K, that means you mainly have reactants present. And so we do use the value of K to help us understand, when this system reaches equilibrium, what we should expect to sort of be there, either reactants or products. Remember that sort of a large value of K is considered a 1 and above. So anything above 1 there is considered a large value. So above 1 there is really considered a large value of K. Any questions on any of that stuff there that we talked about last time? Okay. So looking at a reaction like this, if we wanted to write the equilibrium expression for it, once again, we would take our products divided by our reactants. So in this case, we would take the concentration of NH3, and using the coefficient here will become our exponent. And then we will divide it by the concentration of our reactants. Here, the coefficient is 1. So obviously, most of the time in chemistry, we don't write anything for 1. So that's why there's nothing written there. And that would be divided by the concentration of our H2, which has a coefficient there of 3. And again, that is what that cubed is for. Once again, this is sometimes referred to as the Kc value. If you were to actually calculate a value here, you would need the equilibrium concentrations to do so. So you would need the equilibrium concentrations to be put into there. As we'll talk about in a second, I think, but just so we're looking at it here, there are pretty much 2 things that we do not usually include when we write the equilibrium expression, and that is we do not include anything that is a solid or a liquid. So anything that's a solid or a pure liquid is not included in the equilibrium expression. That is why, as you remember, we talked about that we actually already saw an equilibrium constant. And because water is a liquid, it is just the products in this case. And that is a pure liquid and would not be included. So that's sort of why when we look at something like Kw, which is also an equilibrium constant, in this case, it's just the products that are shown because the concentration of our water there is not going to change. And that's really the reason why these 2 things are not included usually in the equilibrium, because if you have something like water that's a pure liquid, its concentration is going to remain pretty constant over the period of time. And in addition, if you have something that's a solid, it's really not doing much. It's just kind of sitting there, right? So in order for it to do anything, it's got to kind of not be a solid. So anything that's a solid or a pure liquid is not included. That pretty much leaves 2 things that are included. So we do include anything that is aqueous and anything that is a gas. So those are the 2 things that you definitely put into your equilibrium constant expression. Pretty much everything else gets left off. Now, if you happen to have a reaction, say like this, where that is a solid, we'll just say, and these guys are gases. And if you were going to write the equilibrium expression for this, in this case, you would actually just do 1 for the products over the concentration of A and the concentration of B. So if you happen to have nothing on the product side there, you just do 1 over the reactants basically when you write the expression to do the equilibrium constant. Any questions on that one there? All right, so as I mentioned, K has the same value at a given temperature. Once again, that is the only thing that will affect the actual numerical value of it. For a given reaction and temperature, there are many equilibrium positions, and that's what we were just talking about. Again, you could start with, all products, reactants, a little bit of everybody. It will always come to rest with the same proportion of products to reactants as long as that temperature remains constant. So that's basically what it's talking about here. So for example, here, consider the following. If we wanted to write the equilibrium expression here, we once again would look at our products, and it would be the concentration of H plus times the concentration of acetate divided by the concentration of acetic acid. And it looks like, I'm assuming the one that's box looks like a winner in that case. Once again here, all the coefficients are 1s, so you don't have to put the 1 in. Again, if you see an equilibrium expression written and there's no number next to the little brackets, it's assumed to be 1, so it's not 0 or anything like that. All right, so let's take a look at this one. For the reaction below, calculate the value of the equilibrium constant given the equilibrium concentrations. So once again, here we would write our equilibrium expression, which is our product. So this is the concentration of NO2. And again, here we do need to square it because of the coefficient, divided by the concentration of N2O4. Coefficient here again is 1, so we don't have to worry about it. In this case, we are given the equilibrium concentrations. So at that point, all we would have to do is plug them in. And I'm going to go with hopefully their answer, which is right. I hope. Double check. You never know, I suppose. 0.06 squared divided by 0.055. Going to give us 0.065 here. So remember that there are no units associated with the value of K. This would be considered a small value of K, yeah? So this would be considered small. And that means that when we do reach equilibrium, we would mainly expect to have reactants present, basically, because of the small value. Any questions on that one there? All right, so there is different types of equilibrium. There's homogeneous equilibria, which is pretty much like a homogeneous mixture, which means everything is the same throughout. So what that essentially means here is all the phases are the same for your reactants and products. So again, here, if we look at our first one, we have gases all the way through. And if we were going to write our K for this, this would be the concentration of our NH3. And again, we would square it because of our coefficient, divided by the concentration of N2 and our H2, which would need to be cubed because of that. Here, we also have all aqueous, which means if we were to write our K, it would be the concentration of H plus, Cn minus, and HCN in this case here. For the top one, because they are all pressures, you could write, again, a Kp for this one, which would be the partial pressure squared of NH3, divided by the partial pressure of N2 and the partial pressure cubed of H2. Bottom one, no Kp could be written because there's no gases. So obviously there's no pressures, so you couldn't write any type of Kp sort of expression for it. Any questions on either of those there? Now, heterogeneous equilibrium is basically the opposite. You basically got a little bit of everything sort of going on. You have things in different phases. So as we mentioned a second ago, the two things that we really do leave off in this is going to be our solids and our liquids. So when we would go to write our equilibrium expression here, actually for the first one here, our K would be the concentration of O2, and it would be cubed. Everything else there is a solid, so it would not be included in this equilibrium. And on the bottom one there, our K would be the concentration of H2 squared times the concentration of O2. And in this case, that is a liquid, so that would not be included either. And this would be what our equilibrium expressions here would look like. So once again, solids, if you think about it in a solution situation, they're kind of sitting there like a rock on the bottom. So there's no way for them to really interact or sort of react. The only way for a solid to be able to react is it would have to dissolve, which means it would no longer be a solid. It would then be like an aqueous ion, and then it would sort of participate. But in this case, just a solid by itself is not going to do much but hang out there and try not to get in the way, I suppose. Any questions on that? So the position of our equilibrium, again, no solids or liquids are going to be dependent on it. So we do leave them out. They will remain constant through here. So here we have something like calcium fluoride, and it's going to make our two ions here. And we again would write our equilibrium expression, which is K would be our calcium ion times our fluoride ion. And again, we do need to square it This is a solid, which means it's not going to be included. This actually is what is sometimes referred to as a KSP type of equilibrium, which means solubility product. So there's actually equilibrium constants for things that, if you remember your solubility rules, there are lots of things that are insoluble. So even though things technically are insoluble, everything will break apart a little bit. So even when we look at something like, say, silver chloride, and it says on our table that's insoluble, you'll get a solid. And that is true, but even with that solid, a little bit of it will part, a super small amount of it will come apart, and you will have a little bit of free silver ions and chloride ions still floating around in that solution in equilibrium. It's just mainly staying over on the reactant side together is why you see it as pretty much being insoluble. And KSP is an equilibrium constant for things that are typically found to be insoluble. So a lot of times when you come across these type of guys, you usually have solids on your reactant side and they're never included in the equilibrium expression. So that's something you'll learn in 1B when you get there. Sometimes, again, we think those solubility rules are 100% always correct. And they are in general sense, but there's a lot of factors that come into play in terms of solubility. Things like concentration, pH, as you learn about, common ions and things like that. So just because necessarily solubility rules say that you should see a solid, the conditions are very important for whether or not you actually will see a solid or not see a solid. And you'll learn a lot more about that when you take 1B later on. All right, so let's talk about Le Chatelier's principle, which we did that sort of experiment. And Le Chatelier's principle is the idea of we have a system that is at equilibrium. So we have this system that is at equilibrium. And basically what you do is you screw it up pretty much. You add some type of stress to the system. And when we add stresses to the system, there's a big categories of stuff that you could do. Much like the experiment we did, you could play with the concentration is one sort of stress that you could play with. You could also play with the pressure and volume if you're dealing with gases. You could also play with the temperature. And you could also do something like add a catalyst or something of that nature. So what happens when you sort of stress out a system that's at equilibrium? What's going to happen is it's going to want to get back to that equilibrium sort of state. So you're going to do something to it that's going to screw up the rate of the forward reaction and reverse reaction being equal to each other. And what's going to happen is it's going to want to get back to that. So when you do that, it will then want to get back to an equilibrium state. And really, there's a few ways that it could do that. It can do what most people refer to as shifting to the right, which means you're going to make more products. It may shift to the left, which means you're going to have more reactants. There are certain things that you could do that even though you sort of did something to it, will actually cause no change to occur. So it'll just kind of hang out where it's at. It won't go one way or the other. So this is essentially what you did in that experiment. You added a little bit of something. It caused the equilibrium to get messed up. It shifted one way or the other to return to equilibrium. In the case of our experiment there, you were able to see different colors. So you knew kind of which way it went, either to the right or to the left. Means you made more reactants or products. So let's talk about each of these and sort of what happens when we do this. So the first thing is concentration. And there's pretty much two things you could do. You could either add more And typically when we add more, we can have it will shift away from the side you added it to. The other thing that we can do with concentration is removes. And in that case, it will actually shift towards the side you removed it from. Now, when we talk about sides, we're really talking about when you look at the balanced equation, did you add more reactants or products, or remove reactants, remove products is what we're looking at. So the adding part is pretty simple, as we did in that experiment. You pretty much just go grab a reagent off the shelf that has a ion or something like that that's similar in your reaction that you're dealing with, and you just scoop it in there. Or if it's a solution, you could add some more of it in there as a source of it. Removing usually involves one of two things. To remove usually involves either making a solid or a precipitate, or making water. So those are two common ways that you can essentially, if you have a solution, like reach in there and take something. And that's because, as we just talked about, if you make a solid, it's no longer going to be part of the equilibrium, right? So it's like, again, reaching in there and taking out those ions from the solution. And if you make water, that's typically a way that you can remove something like hydroxide, OH minus, or H plus from the reaction if you have either of those. And you can do that by adding an acid or base to do that. I think we had one of those in that experiment as well with the chromium, I think. You had hydroxide, you had an acid or maybe a base to it to go one way or the other in that particular case. Bless you. So if we just think about this again, sort of with our little stick figures here, and if we have a system that's at equilibrium, and once again on the left here is our reactants, and this will be our products, and we're at equilibrium. If somebody does sort of hop on here on the product side on this little teeter-totter here, it's going to cause this effect to occur, which is going to really kind of screw up the equilibrium here. And now in this case, to fix the situation, we actually need to put more people on the left-hand side. So we added people over here. So to fix it, we would have to shift to the left there and put more people on the left-hand side to bring it back to equilibrium. And when it does so, we will be back to our second equilibrium position here. And we're back to equilibrium. So if you add more products, it will shift to the reactant side. The real reason for that is when you add more products, there's more products available to react with, which is going to cause the reverse reaction to occur. And that's why you end up making more reactants in that case. Same thing if you added more reactants, that means there's going to be more reactants available to react with each other. They're not going to have to go find each other. There's a whole bunch of them ready to go react. And that's going to cause the forward direction to occur. And that's why you actually make products in this case. Now, if we have the equilibrium like so here, and again, this is our reactants and this is our product guy over here. And if our product guy hopped off, we're going to end up with something like this. In this case, to fix this, we actually removed over here. So it actually has to go towards the side we removed it. You could kind of think of it as if you remove something like you made a hole on that side and you got to fill it. So it's going to go towards that side to fill the hole. And when it does so, it will once again return to equilibrium here. Position. And the real reason here is the same sort of explanation. When we remove our products in this case, that means that we have more reactants, which means that our forward reaction is going to occur, which is going to make more products. When we would remove reactants, we would actually again have more products, which means our reverse reaction would actually take place and we would make more reactants in that case. Question on concentration. So the other couple of things here is pressure and volume. They are usually kind of tied together in a lot of cases. And it also goes back to our friend Boyle's law, maybe P1 V1 equals P2 V2. In this relationship, as the pressure goes up, the volume goes down, right? And vice versa. So in a situation where you have gases, if the pressure goes up, the volume will go down. So the sort of change that occurs here is the pressure starts to go up. We kind of want to bring it back down, but now we have a much smaller volume. So because of that smaller volume, we actually will need less gas molecules. Otherwise, there will be the same number of collisions. So it will shift to the side with the least number of gas molecules. And that is obviously dependent on the reaction you're looking at as to which side has the least number of gas molecules. You would look at everybody that has a G next to it and the coefficients and pretty much just count them up and see how much you have on each side. Now, if you do the opposite, if you lower the pressure, that usually results in a much larger volume. So what's happening here is the pressure starts to drop. You want to fix it by bringing the pressure back up. But now we have a much larger volume, which means we actually need more gas molecules to fill it. And it will shift to the side with the most gas molecules. And again, it is dependent on which side that would be, depending on the reaction that you are looking at. I personally, when I think about pressure and volume, always think about the volume part of it. All you have to remember is small volume, less gas molecules, larger volume, more gas molecules. And that's the way, a good way to sort of think about it. Question on that there. So if I had something like, and in this case, let's say I added C, I removed A, I decreased the volume. Which way will this reaction shift? Will it go to the left? Will it go to the right? Will there be no change? So take a moment. So for each of those, decide which way it will shift. Okay, so let's take a look. So first off, we're going to add C in this case. So that essentially means that we're adding more products, and that means there's going to be more products to react, which is essentially going to, when we add, it goes away. So it should shift here to the left in this case. And that is because more products will actually cause the reverse reaction to occur because they're going to react a lot easier. And that's going to cause more reactants to happen in this case. Any questions on that one? Here, if we look at A and we remove A, which is our reactant, that's going to essentially create a hole on the side where A is at. And what that also will mean is we will now have more products than reactants. And that's going to also cause the reverse reaction to happen to fill that hole that you just made on that side. It will go towards it. And in this case, it will go to the left in this case. Lastly, here, if we decrease the volume, that means that we would expect the pressure to go up. And to kind of bring the pressure back down, in this case, we actually want less gas molecules in that smaller volume. So small volume, less gas molecules. So if we look at this is a gas and this is a gas. That's a 2 and a 1. So there's 3 gas molecules there on the left-hand side. Right-hand side, there's just 1, which means in this case, it will actually shift to the right in this case, towards that side that has the least number of gas molecules. Any questions on any of that there? Okay, the other sort of major effect on equilibrium is temperature. And temperature works the same as concentration, which means if you increase the temperature, it will shift away. And if you lower the temperature, it will shift towards it. So what determines sort of which way that's going to be? It is the type of reaction that you're dealing with. So there's two types of reactions that we deal with, which is exothermic reactions. An exothermic reaction means that heat and energy is given off. And when we think about an exothermic reaction, not correct in all aspects, but we think of heat and energy as being a product, like it's being given off. So when we have an exothermic reaction, we think of heat and energy as being a product. The way that it is commonly sort of represented to you in problems is through our change in enthalpy value, which will be a negative value. So if you see a delta H value with a negative sign, doesn't really matter the number, but the negative will tell you it's exothermic, and you'll know that it is that type of reaction. Now, endothermic is the opposite. Heat and energy is absorbed. And when we have an endothermic process, we think of heat and energy as a reactant rather than a product. And the delta H value here is usually a positive number, so it is considered a reactant. That means if you have an exothermic reaction and you raise the temperature of that reaction, it would be like adding more products, and you would expect the equilibrium to shift to the left. If you take an exothermic reaction, you put it on ice, it's like removing temperature, and it would come to the right-hand side in that case, towards the temperature value or the heat value. And it would be opposite for endothermic. If you have an endothermic reaction and you increase the temperature, it will shift away from the reactant side. And if you decrease the temperature, it will come towards the reactant side. And again, it works basically the same way. Add away, and if you remove it, goes towards it, right? Any questions on that there? Last thing that you can kind of do is add a catalyst. And a catalyst, as we've talked about, is again not a reactant, it's not a product, it does not get used up. So what it actually does in a shifting of equilibrium is it will actually cause no change to occur. So that's one of the ways that you can get kind of like a no change to occur. The reaction will just occur faster, but it will not cause a shift either way. The other two ways that you can commonly come across something that will cause a no change is if you perhaps added a noble gas. Noble gases are unreactive, right? Chemically inert, so they will not do anything. The other way is if you had a gas equilibrium like we were talking about. So let's just say we had this as our equilibrium. Maybe put a letter there. That would be good. Goes to say two of these. So you have two gas molecules on the left, two on the right. And if you change the pressure or volume, there is no side that, right? There's no small gas molecules, larger gas molecules, they're equal. So that's another way that you could get a no change if you have kind of equal numbers of gas molecules on each side. So it is possible to get no changes, and those are kind of the three common ways. You add a catalyst, a noble gas, or if you have the same number of gas molecules on each side of the arrow, they essentially will cancel each other out. Any questions on that there? So let's take a look at some here. Let's just have, we'll do the delta H here is, I don't know, we'll go with, we'll do a positive number. Why not? 125 kilojoules. Definitely not the right answer number. All right, so on this case, what we want to know is if we have this equilibrium, will it shift to the left? Will it shift to the right? Or will there be no change? If I do the following, I increase the pressure, I decrease the temperature, I add more N2, I remove H2, I increase the volume, I increase the temperature. I add a catalyst. All right, so for each of those things, we're going left, we're going right. Will there be no change in this case? Okay, let's take a look and see. So we'll start the first one. We're going to increase the pressure, which means really my volume is going to go down. So I'm going to have a much smaller volume. So as we talked about, small volume means that we do want less gas molecules. So in this case, on this side here, we have 4 gas molecules, 3 and 1. On this side, we have only 2 gas molecules. Which means this guy will shift to the right in this case. Any questions on that one? Looking at the next one, we're going to decrease the temperature. I could look at my delta H value that was given to me. I really don't even need to look at the number, but I do see that it is positive, and that means that this is going to be a endothermic reaction, which means heat and energy would be considered a reactant in this case. And that means that if I decrease the temperature, that would be like removing a reactant, which means I made a hole on the reactant side. So that's going to cause it to shift towards the reactant side in this particular case. Any questions on that one there? Next, we're going to add N2. So I'm adding N2. That's going to increase the reactants. That's going to cause the forward direction to occur and will cause it to shift away from the reactant side and make more products. If I remove H2, which is a reactant as well, that means I'm going to make another hole over here on the reactant side. So it's going to go towards that hole to fill it, and it would shift to the left. If I increase the volume, that means I have much larger area. So big volume means I need more gas molecules to fill it. And as we earlier determined, left-hand side has more gas molecules, so it will shift to the left in this case. If I increase the temperature, because it's an endothermic reaction, that would be like adding more reactants, which would cause the forward direction to occur, and it would shift away from it, which means it would go to the product side. And lastly here, adding a catalyst, or a cat, I suppose, will mean that we will get no change will occur in this case. Any questions on Le Chatelier's principle?